Okay, while I'm doing this physical work equation, all this story about torturing Boltzmann, that's you have Boltzmann kinetic equation, or you have just second law of thermodynamics. It tells you that the entropy generally grows, not decreases if you're a mathematician. And so if you take a system and just let it evolve, it will somehow come to a larger entropy. On the other hand, if you look at the equation of motion, whether classical or quantum, they are time reversible. Also, if you write Hamiltonian equations, they preserve measure, and so they conserve entropy. And so this is it's sometimes called reversibility paradox, etc. At least that was how I was tortured when I was a student. Somebody thinks that this is totally trivial and know clearly. I mean, how many people raise your hand if you think that this is a trivial point? There's nothing to talk about. Everything is clear here. Don't be afraid again. If you see, I think that it's trivial, for example, and there is nothing to talk about, and as I said. But okay, so if you don't think it's trivial, then I spend some time. I promise you to be quantum today, give you black holes, all this fancy stuff. But before, let's save Boltzmann from this torture. And so let me say a few words about why I think there is no paradox here and that it's really totally trivial. One of the reasons that I started to teach statistical physics as an information theory because I hated the way they taught me when I was a student. They taught us all this reversibility paradox, return paradox, that there is this Poincaré theorem that every dynamical system returns to it, how it can return if entropy only grows. It's all total nonsense, and let me explain it to you, okay, briefly. So if I just look at the particles in a gas, there are many particles, n of them. And generally, you can ask what is the probability distribution of these particles, let's say, over their momenta. So this is some function of momenta. And you can write an equation for this, assuming that it's a very rarefied gas. And there is some collision integral. But what stands here, a 2-point correlation function between two particles. Because how particle can change its momentum, it can change because it's collide with some other particle. So there will be some kind of a second moment or second cumulant. I'm deriving Boltzmann equation, which you've seen many, many times. So what Boltzmann says is let's just present it as F1, F2. So we break this, assuming that they are independent before collision. So they come from very large distances, dilute gas. So they are independent. Then it's a closed equation. It's a function, one particle function. It's one particle function. It's one particle function. And this particularly equation has this statement that ds dt is larger or equal than 0, where S is, of course, the sum from I1 to N of entropies of different, let's say it, SI, of different particles. Okay? On the other hand, if you look at this dynamical system, then you can say that whatever, distribution, even if you look at rho, which depends on P and Q of all coordinates, that what Bernard writes like every 5 minutes, it's always a continuity equation, right? Because rho is a density, the integral of it, it's probability, right? So it's you integrate, it's the integral is conserved. V is a vector which is Q dot P dot, right? So you can always write, and I'm a fluid mechanicist, I always like to write this equation as minus V grad rho minus rho div V, or you can take this, put here, so it tells you that the derivative along the flow is minus rho div V. But what is div V? V has two components, Q dot and P dot. So divergence, it means that you take dq dot and differentiate it with respect to Q, and you take dp dot and differentiate it with respect to P, right? But then what is Q dot? It's Hamiltonian equation, so Q dot is dH dP, and you differentiate it with respect to Q, and then you differentiate with respect to P dot, but P is minus dH dQ, so it's 0. As we say, that the Hamiltonian evolution of phase space is an incompressible flow. So this is 0, which means that this is 0, right? That's so-called, like in 4 minutes, it's what is called reversibility paradox or Liouville theorem paradox. On one hand, any evolution along in phase space preserve density. That's called Liouville theorem. On the other hand, Boltzmann equation tells us that the entropy must grow. How would you resolve this paradox? Using all I taught you in last 2 lectures. I already gave you the instrument which makes this stupid question, namely trivial. The answer to this question is trivial. Huh? So now, what really, how to say that, well, come on, I mean, what let's talk about? So, system is isolated. This isolated system, look. Is there any contradiction between saying that the Boltzmann entropy, which is the sum of individual one-particle entropies, that's what Boltzmann equation is written about. It's written about one-particle probability distribution. Boltzmann entropy is the sum of one-particle entropies. What is Liouville entropy, which comes out? Liouville entropy is just integral rho log rho over dp dq, right? Minus. But it's an n-particle entropy. It's an entropy of the whole distribution. So what we have here, and that's why knowing this magic words, mutual information, is so important. It's like you switch light in a room and then you see everything. So what essentially you see here, that the total entropy is conserved, but the sum of individual entropies is not. But they are not equal to each other. And never been, even in the 19th century. They never been the same thing. And what is the difference between them? What is this magic quantity S of A plus S of B minus S of AB? Or in this particular case, the sum of Si from 1 to n minus S of P1 Pn. What is called mutual information. So that's how you make science powerful. You make it trivial. So this is a trivial statement that if you, following Boltzmann, assume that particles were non-correlated at the beginning. The Boltzmann equation is written for initial state of uncorrelated particle. Then you let them collide, and what will happen? They start being correlated. So you would have this guy growing. You have this guy conserved. That's called Liouville theorem. What, as a result, you obtain about Boltzmann entropy would be growing. That's nothing. It's trivial. Okay? As long as you understand that the entropy is not a sum of individual entropies. You can put it at the beginning. It could be. In a moment, we start talking about quantum thermalization and all this. This would be a particular case of it, but much less trivial because of entanglement. But the whole idea is the same. You can start from a state which is uncorrelated state. They don't be surprised that the correlation would grow with time. But if you now try to describe your system by the sum of individual entropy or of parts of your subsystem, okay, that would also grow, because this is grow. You know, some things are very important in life, like, I don't know, love, money, second law of thermodynamics, which means that you need to have your own personal attitude towards them. Don't trust anybody. That's a very important message. Yeah? Some things are very important in life. You cannot believe, when people say, money is this or love is this, don't trust them. Try. Make your own attitude. So my own attitude towards, it took me a lot of time to understand. And then I start teaching it, where is the book? Right? So this is the way you look at second law of thermodynamics. You can look at it and say, second law of thermodynamics is just a Liouville theorem. It's a conservation of total entropy. It's equivalent to the statement that the Boltzmann sum grows. I actually have two ways. My own, I mean, not my own, there are great people, of course, did it. It's just the way that another way, for example, of looking at second law thermodynamics is not saying that delta S on average is non-negative, but saying, and of course this is only for particular classes that I can prove it, that's equality, but because exponent is a convex function, then from here follows this one statement, okay? That's also second law of thermodynamics. So you can formulate second law of thermodynamics as a known decrease of Boltzmann entropy, or you can formulate it as a conservation of a total entropy, which includes correlations, okay? Good. So now forward to H bar. Questions about it? Excellent, excellent. This is a very good question. It, in a sense, shows you a different way to increase entropy. And this is the way which is related to dynamical chaos. Again, I did not want to go with you, but as long as you ask, I want to go with you. So you can say, okay, I'm in the phase space. What it means system? This is a space which has 3n momenta and 3n coordinates, like this is a huge space, right? And particles, each one has 3 coordinates and three momenta. But a system is a point in this space. But see, I don't know exactly the coordinates, right? And now I look at a given volume. So what happens? Look, it's a Liouville theorem, which tells me it's incompressible flow. Incompressible flow, it would go somewhere, it will be stretched in some direction, and it will be expanded in another direction, but I still look at it with a finite precision. This is my finite precision. As long as I look at it with a finite precision, what I will see effectively is that its phase volume grows. Not because it grows in some sense of loss of motion. Okay, at this point, I have, I was fortunate that some great scientists used to be students who were sitting and listening to lecture. And one of them is Misha Tsodeks, who has made a great discovery, probably will get Nobel Prize for it in brain research. He was when I just started to teach it, like 10 or 15 years ago. And after lecture, he was very excited. He came to me and said, "Are you saying me that second law of thermodynamics is not a law of nature?" I said, "Yeah, of course. It's something between us and nature." Well, Liouville theorem is the law of nature. Second law of thermodynamics tells us the following thing. A perfect knowledge persists. Any degree of ignorance grows. Here, you put your ignorance by a finite precision. Here, you put your ignorance by don't looking at correlations. That's our choice, right? Maxwell was a genius. In 1879, in his diary, incidentally, he did not publish it. He understood, he has a perfect epiphany. He said, if you would be seeing every molecules, there is no need in thermodynamics and statistical physics. God Almighty does not need this science. That's human science. Okay? And the law of thermodynamics is essentially, the way I understand it, only perfect knowledge persists. Any ignorant grows and fills the space. That's what happens over here. Okay? More questions? You know, we physicists, very arrogant people. I mean, look at me. And then when, you know, we look at biologists, psychologists, political scientists, we say, well, this is really kind of, you know, soft sciences. We are really, what we study is kind of truly fundamental. It's not about, look even at chemists. What is organic chemistry, non-organic? What's so special about organic? It's because we are humans, then, you know, organic chemistry is somehow special. But we physicists have truly objective notions. We are working with something not. We also work with something which is human language. Physics is a human language, and theoretical physics is even more so. Okay, forward to H bar. So quantum mechanics, and at the end of this will be relativity. Why would I spend part of information theory course on talking about quantum mechanics or relativity? Is it, I mean, this is a title of my book, it's the physical nature of information. We are not only talking about information as an uncertainty, but it's an uncertainty about physical world. So there is something in physical laws of nature could tell us something fundamental about a level of uncertainty or amount of information that we could miss. And as you probably already realized, it would be mostly about inequalities, restrictions. And of course, each one of you immediately would tell me, and that will be first part of lecture, that of course, the fact that there is H bar in the world means that there is Heisenberg uncertainty relation, right? There, in some sense, it imposes lower bound on any uncertainties that you can have about physical world, right? So the only thing that I will add today is I'll show you entropic form of this, not just a simple thing that you learn in undergraduate. But what is really surprising is that would be the second part of the lecture, that there is also bound from above on how much information could be in, let's say, in any given region of space. Where it would come from? How would you guess? Every time you go to lecture, try to guess what this guy will talk about. Maybe I can kind of skip the lecture and understand it myself. So where this restriction from above can come? The bound comes out of size. It says if you have a region of space of the size R, you cannot put there more information than some very special bound. It's called Bekenstein bound. This is a guy in Jerusalem, used to work, but it was in Princeton with Wheeler. Why would it come? What physical laws would impose? First of all, it's clear why H bar impose restriction, because H bar tells us that you cannot simultaneously measure some things. It already makes it huh? Yeah. Ooh. Yeah. So H bar clearly tells us that you cannot measure simultaneously two things. It definitely increases our uncertainty, right? We need P and Q simultaneously to predict the motion. It tells us you cannot, okay. But now, why uncertainty could not be larger than something? Namely, why there could not be some limit on information which you can encode in a given set of space? I don't see how conservation laws. Let's say, you say, okay, here is this. I just put here something else, and then I put some quantum computer, and then on some quantum dot, and then I put some DNA. DNA is really very dense, you know, package of information. Probably nothing denser than DNA that we have. But I say, no, 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 no. There is a limit from above. Where it comes from? Let's work with bosons. It comes from gravity. That's what really I find. When I learned it, when I was already older than you, I mean, when I was young like you, I was totally, I mean, ignorant person. So I learned it much later. And so that's what I'll tell you about. Okay, good. So let's start from H bar. And you all know quantum mechanics, and probably most of you know quantum mechanics better than me because I'm a fluid mechanicist, essentially. But so I'll tell you how I view quantum mechanics and in what sense I can learn something about information theory from it. For me, quantum mechanics is a trivial discipline. It's mathematically totally trivial. It's just linear algebra. Okay? So all the non-triviality comes out of interpretation of what actually we do, but manipulation itself is very trivial. It tells me that I would have vectors. So what is linear algebra? Linear algebra is about vectors and matrices. That's it. End of story. So we'll be talking about vectors and matrices, and I would sometimes call it vector like this, or I would call it psi I. As long as we have vectors, we need to introduce an internal product of two vectors. And what is really bizarre, but again, mathematically is kind of trivial, is that you can have in vector space some basis, some different states, and system could be in a superposition of these states. This is really something very, very fundamental. So how I would, I would probably like this. So if you have, let's say, W, it could be a sum over I, Wi over this I. And so if you have V, which is the sum of Vi, of Vj, j's, then this internal product, you know what it is. This is just Vj complex conjugated, V Wi, and and just the sum over all i's over here. So those are orthonormal vectors, and then how you do a product. Now, what is important here, and why is quantum mechanics is so bizarre, that they have this idea of a measurement. And for measurement, it introduces the observables. Observable is a matrix. So you would have some matrices, I don't know, or I don't know, Aij, or you can say that this is A. And so you can take A, act on a given space, and if you are interested in a measurement in the state, that what you need to do is to take an internal product. And that would give you, this is so, this matrix acting on a vector, give me another vector. And generally, you can also have something non-trivial in this way, because this acting on this vector can produce some vector which has a non-zero projection on a J, and that would give you your measurement results. Again, my personal view that quantum mechanics is incomplete in the sense that a measurement is not described by quantum mechanics. Okay, so this is something which requires a classical device, which again, I personally hate. I don't like it very much since the very moment that Niels Bohr introduced it, and I would love to have a kind of a general framework in which measurement will be also part of it, and then it's actually probably doable at some point to say that the measuring device has a very large but finite number of degrees of freedom, and that's also quantum object, and then this number of degrees of freedom go on to infinity, and you have what is called collapse of a function, etc. This probably mathematically it's doable, but there's probably already somebody did it, I just don't know. Okay, so now what is immediately comes out as an important part for information theory is that matrices do not commute generally. Just very, very general property. And I knew the guy, Rumer, who was in 1926 in Göttingen, and then in 1976 he gave us like a historical course about 50 years of quantum mechanics. He says that Heisenberg returned from vacation and he shown everyone these tables and said, look, these tables that you actually multiply like this and they do not commute. He did not know matrices. They was not at that point part of education. What does it mean non-commuting? It means the following thing. For example, you have a matrix X which corresponds to measuring some quantity. So you measure it, or then you can measure some other quantity after that. The fact that this is not equal to first measuring Z and then measuring X means that there is no simultaneously the same values of X and Z. Because if they would be, they would give the same answer, namely those values of it. And now, technically, of course, you can use it. Let me just write a trivial inequality, which you probably seen. So if you take any place psi, any state psi, it's a vector. So you take x, z, commutator, which is, I mean, you know what is commutator, right? And you compute this squared, you can always bound it from above by something which would be 4 psi xz, just xz, the product, without any commutator, and minus psi xz plus zx. And then you can always drop this, and you can say that this is less than 4 xz psi squared, and then you can use Cauchy-Bunyakovsky. There was actually a Ukrainian mathematician who derived it a little bit before Cauchy. And so this Cauchy-Bunyakovsky tells you that you can, the squared of a product described as a product of squares, and so you would get x squared psi times psi z squared psi. And this is, of course, sigma x times sigma z. And it's bounded by this commutator. And in particularly, as we all learn, one particular case of this x and z is coordinate, call it q minus q, and z could be p minus p. And because p is e h bar d dx, then this commutator tells you that sigma p, sigma q, larger or equal than h bar times d, where d is the dimensionality, because different components in d-dimensional space, they do commute. It's only p along one direction. So this is the way that there is 1/2 probably somewhere. I always forget it. Now, of course, I already did here. Yes, this is 1/2 here. I did already a very important jump here from this inequality, which depends on psi's, right? So now, taking different psi's, I can kind of get different values. It just bounced from below, but and this is already a statement where there is no, well, this is in this state, so you may ask, what could be different states which take it to the total minimum? What are the state? And then you can do a simple computation which shows you that this is a Gaussian state. Namely, it's a free particle which has its probability distribution of coordinate as a Gaussian, and because in momentum it will be Fourier transform of Gaussian is also Gaussian, so that would bring you to this state. It's a simple computation. You can look in the book how it's done. You probably did it in your quantum mechanics course. So that tells you that you can actually rewrite this expression as an absolute minimum, because a Gaussian gives you minimum variance, but you can say that, well, variance is an exponent of entropy, or entropy of a Gaussian distribution is a logarithm of variance. then you can write it as a log, taking log of this expression, divided your sigma p, the square root of h, divided your sigma q as the square root of h, larger or equal than d, and log d. And so you can write it as s of p plus s of q larger or equal than logarithm of d. That's a modern form of Heisenberg uncertainty relation. I guess it's Deutsch 70s. So it's kind of maybe 60s, probably 70s. So it's a, but then again, as we discussed, this must be a right way. For Gaussian distribution, it's the same. You can talk about variances or you can talk about entropies because the Gaussian distribution is completely determined by its variance. But I really want you as a 21st century people to see that the uncertainty relation, this is the right form of it, the most general form of it. Whatever you have a distribution of momenta, whatever, and it's not necessarily Gaussian, this could be interacting particles or whatever, or particles in some potential that would have non-Gaussian distribution. This is the general form. Okay? A little bit more, I want to look at it again from this perspective of being doing linear algebra. Is it what means the non-commutativity of two matrices? It's if you do algebra, you know that it means that you can take for a given matrix a set of eigenvectors which diagonalizes it, namely just eigenvectors of this matrix, etc. So, and it is in this basis that it does your measurements, right? When you do measure observable related to the maximum, to the matrix X, it gives you one of its eigenvectors at this state. But you can also do it for matrix Z. And this would be a different set of vectors. This fact that X and Z do not commute means that there is no a single basis in which you can diagonalize them both. And that lets you to see this relation in a little bit, to write it in a little bit more general form. Probably I will derive you more general, but I want to derive it including entanglement and entropy. So for now, I just give you a form and then I'll derive it. So what essentially stands here is the quantity which is this thing and taken maximum. Namely, this is a projection of different eigenvectors of Z. This is the eigenvectors of Z. This is an eigenvectors of X. The fact that the matrices do not commute could be presented by the statement that generally any eigenvector of X is a kind of non-zero projection on X. And any projection of X. So generally, this inequality is what is called unbiased basis, namely, if on general you have d vectors this and d vectors z, and if they kind of arbitrarily oriented, then the projection of each to another is just 1 over d, right? Each one has a unit length, and if there are d vectors, so in essentially what it tells, you can, instead of here, write that this is a logarithm 1 over x z projection square, right? So this, in this sense, s of p plus s of, or s of x plus s of z larger or equal than the logarithm 1 over maximum x z. This is the most general form of uncertainty relation, okay? And it's entropic. That's very important. That's the proper language. Is it clear? Yeah.
When you define SQ, log of sigma q divided by it should be a length, probabilistic quantum length. So if sigma is smaller than this length, the entropy could become negative.
Yeah, it's a very good question. In a sense that, of course, what is written here is something which is about what is called differential entropy. So I'm treating it as a continuous Gaussian distribution taking logarithm, which means that it's all up to a factor. Now entropies has no meaning by itself, only differences. Because I'm working, because honestly, I would need to break it into pieces and compute and do combinatorics. So in a sense, what we are saying here is only the following statement. When this is getting larger, this is getting smaller, so that it keeps this sum, okay? But generally, of course, you can say that if you can shrink this, for example, uh, uh, again, it tells you that you can measure with any precision p, but then your imprecision is q will be arbitrarily large. Okay? You all know this, right? I just want you to see kind of entropic formulation of it. Any question? Okay, good. So now, because we want to do information theory, etc., then what will be working is in a thing which is called qubit, and it is something which is terminologically very bad, namely that we physicists used to introduce terminology which does not make any sense except that we get used to it. A randomization group is not a group, and we call it a group, and it's just okay, kind of live happily with it. So bit is a bit, is a binary digit, and everybody understands what it is. Now, when we say qubit, it's usually that we mean a unit of quantum information, and it's now will be not about measurements. No, this is about measurements. It's a usual classical entropy. There's nothing quantum about it, right? You look at a psi function in X representation, you take modulus square, it's a probability distribution, you compute rho log rho of it, that's your entropy. It's totally classical entropy, it's something about measurements. Now we're starting to talking about states, which incidentally quantum mechanics tells us we cannot measure. There is no way to measure state. You can only measure observables, right? Classical things. Okay, so we can live with it, namely we cannot measure, but we can operate it, etc., and measure something afterwards. But so by qubit, we mean both a unit of quantum information about states and a given physical object. Okay, so when every time you see qubit somewhere, you ask yourself, is this guy now talking about spin as a physical object, or I don't know, or photon which has two polarization, right? So this is just a qubit. Any photon is a qubit, right? It can have two polarizations. But so we'll just denote it. Again, it's a vector who can be, has a two eigenstates, and generally every qubit could be in a state of superposition. This is, again, superposition is a very bizarre statement, right? For example, if you take your observable Hamiltonian, then being a superposition means that you can have simultaneously different energy. Because you can be in different states of Hamiltonian, every state of Hamiltonian has its eigenvalue energy, and you can have different energies simultaneously. Well, that's the rule of the game. As they say, shut up and calculate. There is nothing to interpret here. So now, if, for example, you have some kind of a measurement preserve on it, so what you have here is A0 plus B1, and what you have here is A0 plus B1. That's how you compute your expectation of the measurement, right? For any operator. Then what you find out that the result of this measurement will be that you will have, with the probability A squared, you would have 0, 0, that matrix element, yeah? Or, and B squared, you would have 1 or 1, but generally, you're acting by O on 0 can give you a non-zero projection, namely, you have a non-zero, non-diagonal component which has this AB complex plus BA complex, right? So this is now something which you do measure on the superposition of qubit in two states, something which depends generally on the relative phases between this complex number A and B. So quantum state is characterized by complex numbers. Their sum is modulus squared equal to unity. But that's what makes this quantum computation so powerful, that essentially every state of a qubit is a whole complex vector. It's infinite number of bits if you wish, just we don't know how to use it. End of quantum mechanics. We go to statistics. Any questions here? Good. Quantum mechanics in 10 minutes, that's very good. What starts about statistics is the following thing, that you start thinking about subsystem. Okay? So now we'll have A and B, and we assume that the whole composite system A and B is a quantum system, and it is in some state. Namely, it's characterized by a vector. Now, let's say that A is characterized by M vector and B is characterized by N vector. Again, just, So what length of this vector must be? M plus N or M times N? Immediately answer. Again, what I'm trying to teach you is that you aren't students anymore, right? Which means that there is no wrong answers. Every answer teaches you something, okay? So don't sort them out. No, you just answer immediately. So M plus N, Jinshen, or Mn? Mn. Somebody thinks that it's M plus N? All overeducated people? Yes. Of course, it's Mn. And one of way of doing, for example, this Mn vector is to do what is called tensorial product. Tensorial product is a very simple thing. For example, if you have, let's say, a vector AB and CDE, so its tensorial product is AC, AD, AE, and then BC, BD, and BE. I don't know how you, but I always like, give myself a simple example to answer. So this is a tensorial product. So generally, this tensorial product is a way to create a Mn vector. Is it generic or it's not? That's the question. No. Why? Yeah, let's see it. This is something so trivial and yet so important. I mean, you're absolutely right. I just want to give formulas for what you are saying so that we can all see. So first of all, what would be a superposition of this state? Let's take a simple thing like a 2 qubit, okay? So we take 2 qubit, and we have state which is 0, 0, state which is 0, 1, state which is 1, 0, and state which is 1, 1, with arbitrary coefficient A, B, C, D. Of course, the sum of squared must be 0, right? Let's now take a tensorial product of two things. So now if I take alpha 0 plus beta 1 A and make a tensorial product on some alpha prime 0 plus beta prime 1 B. Okay? Which means that now when I take this times this, what I will be doing alpha prime 0, 0. It's always A, it's always B. So the first position is about system. You've seen all this, right? Or anyway, let's just, and then if you do this, this by this, you would have beta prime 1, 1, and then you would have alpha beta prime 0, 1 plus alpha prime beta 1, 0. So now if you compare with this and this, you notice that here, if you take this and multiply by this, so this is your A, this is your B, right? So if you multiply this by this, you would get the same if you multiply Z by Z. Namely, tensorial product requires that in your general thing this is equal, and generally it is not. Okay? So this is a simple example to tell you that when you have a composite system and its most general state is a superposition, it generally cannot be presented as a tensorial product of two superpositions for different states. Okay? Is that clear? That's how entanglement appear. Okay? That's now means that generally you need to take here k and sum over k. And traditionally it's called, you can introduce these eigenvectors, make them all positive, and you do it like this. Should not be a double sum then, maybe. Why it's a single sum? So what follows from here, and I don't prove it, but it's clear already that I cannot do one tensorial product, I need at least to add. But why I don't write something like psi I times psi bj alpha ij and sum over ij? That would be even more disastrous. That would be a double sum. Why I write a single sum? Well, you all seen this, right? Because you've learned quantum mechanics and quantum statistics. I'm not telling you, because I'm not going, I cannot teach you in 15 minutes. So I assume that you learned it, and I'm trying to see it. Yes, exactly. It's called Schmidt decomposition or singular value decomposition. You can, if you write it in this idiotic form, you can always present this alpha ij as some kind of vik dk and wkj, where d is diagonal, right? It's called singular value decomposition, and then you introduce, you multiply psi by v, you call it in u psi, you multiply this by w, you call it in u psi, and then you can write it as a single sum. It's really an important point. I just do this, or you can find it in the book. Okay? So what we now come, and this was realized by a PhD student. Who else? I mean, most of the things was done by PhD students. So this was done by PhD students who was also just 19, Lev Landau, in 27. He realized that generally what you do, you need some kind of a general sum. And that led him to introducing what is called density matrix. Namely, this is something which you now try to answer the following question. What would be if I try to compute a measurement only on the subsystem A? Okay, so now what you do, you just take this sum and substitute it, and then what you do, you say that I'm going to compute the following thing. This we already agree that we don't need, thanks to Schmidt. And so I'll write now the formula, and it will be exactly 12 o'clock, and we go for the break. And so during the break, you can come and compute this formula, and then I'll come back and we'll continue. Okay. So what is the formula? Well, now I am saying that I'm having a sum of a pj psi a j psi b j. I'm taking, or I'm measuring only on A, which means that on B, I'm using identity operator, which does not change anything with B, just leaves the same states, right? And so what I do here is, here I have something over I. So generally, this is sum over J, sum over J. But here is sum over I, which is psi AI, psi bi. square root of pi's. So that's what this PhD student, being in Leipzig, I guess, at this time, he came out of Russia to do his PhD in Germany, like many other people, 100 years later. And those is formulas that he wrote, and we now go for a break, and then we'll come back and compute it, okay? Okay, let's go. We don't have much time. If you want to hear about black holes, then I would really need to proceed fast now. So what you do over here, that what Lev Landau did in 1927, is that you now make this I acting on this psi and this psi, and because it's an identity, it does not change any of these eigenvectors, which means that it produces delta ij just by this part, right? So after the delta ij, you would get j equal to I. So what you eventually would get, you would get this giving you a single sum and not a double sum, and it would be a sum over k of this OA acting on psi k and acting on psi k, and which means that you get a trace. You see, it's a diagonal. So generally, you have this like ij, but when you compute any measurable, you take a trace, but that it is a trace of what? And it's a trace of a matrix, which you can now, let's say, so generally you have this matrix which you define and is called density matrix. Again, a very bad name, but it's kind of stick to it. And as some people asked me, I mean, there were a lot of young students in different cities of Germany, but everyone come on Sunday to von Laue's seminar. And von Neumann, who was at the time PhD in mathematics, doing his PhD in mathematics and in chemical engineering in other countries, so he was kind of he was PhD student in 2 different countries at the same time. Doing one of the reasons is all these people were able to do a bomb, but they were simultaneously physicists and chemical engineers, mathematicians and chemical engineers, because chemistry was a profession, right? It was real something that people needed, and physics was kind of back then. So, and then von Neumann says that if we have this matrix, then we can do with it, with this matrix, the same thing that we do with usual distribution, is namely that we can define an entropy of any matrix in the same way as taking rho log rho, and because the sum of all this, and because this is all matrices which are diagonalizable, then again you can think of this matrix as just matrix which have an logarithm of these values. I'm not going to go into much details here. I just want to give what is the meaning of it. So in a sense, what Landau tells you the following thing, that if you have a quantum system, composite system, A-B system, which is characterized by a vector, but it's a very long vector, right? So it has this kind of, it has sum of tensorial products. The moment that it's not a single tensorial product is an equivalent of independence. If there would be no sums here, right, it would be a single product, then you would be characterizing A also by a vector. Now, because there is sum over here, then you're characterizing A by a matrix. And that's something which is a new way of describing uncertainty. In classical physics, we describe uncertainty by a vector of probabilities. It's a set of positive numbers. Their sum is unity. You can think about it as a normalized vector. In quantum mechanics, we characterize state by a complex vector, generally complex, but it's a vector. In quantum statistics, because of this fact of entanglement. Entanglement means that in this sum over K, there is more than one term. That's it. That's the meaning of word entanglement. Okay? And now what this matrix, it's a matrix made out of states of A. Why? What Ig element of this matrix tells you? It tells you how state I and state J are actually correlated through all states of B, like possible correlations. And to make it really bizarre is that B could be the rest of the world, right? So in this sense, that Gibbs entropy and Boltzmann entropy, in a sense, count possible number of microstates which are compatible with the macrostates that you observe. For Neumann entropy counts possible number of states in the environment, in the whole rest of the universe, compatible with any measurement that you can do in your A. Okay? So this is kind of a, but it's again something which is hidden. And it's a result of what? What is the physical reason that I cannot forget about B? It's Heisenberg relation. Heisenberg relation, its most important qualitative message is everything is non-local. You know, your phase space is P and Q, right? You want to describe something, but you cannot. In P and Q, you have finite domains. You can make it sharper and sharper and measure beta and Q, then it will, in P will be this. So essentially, the quantum mechanics has this very deep non-locality, and this deep non-locality in particularly manifested in the fact that you cannot separate A from B. Well, some system you can. There are states you can take A kind of very far and then bring it to B, and then at this point they start interaction, but at the moment that you start, it's a tensorial product. Tensorial product exists, but generally what it tells you, that there also exists state in which information about A is encoded non-locally. And the moment that you try to create this matrix, how you create it? You trace out all the B components of your Mn vector. At this point, you find out that some information about A was encoded in B and you lost it. Namely, average of all possible states. At the moment you lost it, you cannot characterize A by a vector. You now characterize it by a matrix, which means it's much more uncertainty. We already discussed on a very superficial level. Okay, there is much more uncertainty in this state, which means that it could be that it's in this state, or it could be this state, and the density matrix tells you about so-called mixing state. So in terms of description, quantum pure state is a vector, mixed state is a matrix. Okay? And now I really wanted to derive it. Unfortunately, I cannot. So let me just write it. Yeah, and you look into the book and you'll find it. So the most general relation about entropy of X and entropy of Z, which are generally non-commuting, right? It's something that you can do the following thing. You have some raw state described by a density matrix, right? And now this is a state, it mixed state described by density. Those are operators. What you can do, you can do different things. You can act by X, or you can act by Z on row, or you can act by XZ on row, or you can write by ZX on row. Okay? What the general relation tell you the following thing, that this sum is always larger or equal. First of all, that S of rho, by it is. If you have a density matrix and it's more than one, it's matrix, not because if it's only one quantities, and its eigenvalue is unity, and the logarithm of it is 0, and von Neumann entropy is 0. So it has its own matrix plus logarithm 1 maximum x z squared. It takes, you can look in the book, it takes half a page to derive, and this is the most general uncertainty relation. Here both sources of quantum uncertainty come together, non-orthogonality of your measuring things, and something related to the state. If you're in a pure state, this is 0. If you're in a mixed state, it's a matrix and you have some component. Okay? So that's what I wanted to give you about quantum statistics. And now questions, and if not, then we go to black holes. Yeah. I mean the following, this is a classical object, namely, I have an observable X. I do all types of measurement in this mixed state. It is a probability distribution of all the results of measurement. This is the Gibbs entropy of this statistics. Statistics of X measurement. This is statistics of Z measurements. This is von Neumann entropy, which distinguish your mixed state from your pure state. Because this exists also in a pure state. Then it would be like this. Okay? That's Heisenberg, that's von Neumann. That's together. Okay? Questions? Okay. So now what I want to tell you something really bizarre and interesting, namely that the true fundamental restriction also come from a very existence of relativity. Oh, no. This is, without entanglement, this is 0. The von Neumann entropy is non-zero, only you have entanglement. Entanglement means simple statement. In this sum, there is more than one term. That's a meaning. That's a meaning. If rho is not a matrix, but a vector, it's 0. That's, and also, von Neumann invented, I mean, again, he met Landau in Berlin at the seminar, and in a few months he published, it's the same 1927, Landau's paper and von Neumann paper. Then von Neumann wrote a book. Some young people write books about it. His original argument, how he introduced his von Neumann entropy of this matrix, is very, very non-trivial. I did not find it anywhere. I was finding kind of explanation which looked to me non-convincing. So what I really did, I went back, found this book, and it's translated into English. I don't read that well German. So I've read it like 50 times. It's absolutely beautiful. You really see how genius thinks in a very, very simple term. Quantum mechanics existed a year and a half at this point. That is 1927. And he already very deeply understands how bizarre actually all this, because he was a mathematician, there was linear algebra. And so I try to explain it in my book the way that I see it. So if you're really interested in how von Neumann introduced von Neumann entropy, look in my book and then look in his original text. It exists on the internet, nowhere else, and it's a very beautiful, maybe 20 pages. And in my book, it's like half a page, which means that I try to condense it. But it's really very beautiful argument. It's about mixing quantum gases. It's a Gedanken experiment. Okay, done. Now what I want to tell you something really strange, the restriction from above on the entropy, which could be encoded, and any restriction comes from physical restriction. And physical restrictions that we have is the following one. You cannot move faster than light. Any restriction, and this what I find really interesting is whatever you find in your particular system you study, you see restriction, ask yourself what is the projection of this restriction into possible information or entropy or whatever. This restriction always must mean something. So let's ask ourselves what it means that you cannot move faster than light. does it mean something about your uncertainty about the world? Any idea? Reduces. How it can reduce is, for example, you are interested what happens in Proxima Centauri, and this tells you that, sorry, guy, you cannot learn what happens in Proxima Centauri until 200 million light years after it. So at least in space-time, it marks black some regions for which, sorry, you just can't learn nothing. It already increases your uncertainty about the world, right? Yeah. Now you can connect it with another. So again, what we did so far was H. Now we added C. But there are three fundamental constants in the world. So you can say, look, there is a third fundamental constant, which is, there are only three fundamental constants in the world, guys. There is, huh? Yeah, absolutely. Gravity. That's it. There are no other constants. Everything else just depends on units. These are kind of fundamental. So you can say, look, the fact that there is gravity, it means that there is an energy that if you take mass m and you can take mass m and they are at this distance r, so if you want to escape from mass m and you have your mass m at a distance r, what you need to have, you need to have your mv squared over 2 larger than this potential energy if you want to go out, right? But then again, it's less than mc squared over 2, which tells you that your radius must be larger, which is called horizon, right? Over here, so you put this here, you could put here, your mass happily disappears. And so this horizon is gm divided by c squared, and I won't write factors like 1/2 pi or whatever. So, but what it happens if there is an object for which its size is less than its horizon? Then nothing could escape out of it, and such object is called black hole. Okay? So essentially, this is something which is, at this point, is purely classical, and it tells you that now you can say, well, but there are three constants, right? So far, what is here is this and this. Incidentally, I already told you that physicists are two-hand people, which means that we do have Newton gravity, which is one constant theory, special relativity, which is one constant, it's a C theory, quantum mechanics, which is one constant theory, quantum electrodynamics, which is two constant theory, HC, general relativity, which is two constant theory, CG. We don't have theory for three constants. My explanation is that we don't have a third hand, so we need to grow up a third hand so that we can, not like in a free energy, E minus Ts, we need a third hand to handle three constants. So far we don't have a theory, it's for your generation to do it, but we have some kind of, partial guesses of what's going on. And so we can say that, I mean, look, if I have this black hole and it has a horizon, is it really isolated? Because the moment I introduce H bar, it tells me nothing could be isolated. That's a message of quantum mechanics. Nothing could be isolated. Okay? It's always mixed. So if we're outside VA and this B is inside of a black hole, sorry, we somehow related to it. And how we related was introduced by another PhD student. I'm sorry, but this is how it works, right? Wheeler was an advisor and Bekenstein was a student. And I very much, Bekenstein was kind of, I knew him, he was a shy guy. But Wheeler wrote in his memoirs, and also on YouTube, I guess there are a couple of videos where already very old Wheeler, but everything he tells is very interesting. Wheeler explained how actually, then Bekenstein, Wheeler asked him, what if I drop something into a black hole? I dropped it there, okay, nobody, no uncertainty, right? So I just decreased uncertainty in this world. As Wheeler said, Bekenstein was visibly disturbed by this idea, And in a couple of months, he came back to his advisor and said, no, you cannot decrease uncertainty in this world. Again, it's a religious statement, right? Uncertainty only is non-decreasing function because a black hole has an entropy. And what you break, you drop something there, you increase its entropy. Okay, how you actually increase its entropy? It's, you again probably heard the story, Stephen Hawking realized that the black hole is actually does radiation. And if you want to see some kind of a physical mechanism, you may say that quantum vacuum is not really empty. Like it consists of always appearing and disappearing. You can have a particle, antiparticle, then they disappear because for a short time, your uncertainty allows you to have out of vacuum creation. Delta E times delta T larger or equals than H bar, so you can have for very short delta T some kind of energy appearing out of nothing and then disappearing. If now you imagine that this straddles the horizon, namely one appears here and another appears here, then this could escape. And this radiation. But because they appear together out of a vacuum, they are entangled. Okay? And so what we are now will be not computing. I will hand wave my way into show you some formulas, will be about entanglement entropy of a black hole with its environment, understood in a very non-trivial sense, that you need to take the entropy of a vacuum without any black hole, which is infinite, and subtract the entropy of a vacuum with a black hole, which is also infinite. And the difference will be finite. This type of manipulation in all this part is really not very easy to do, so you just do it for like many years and then you get used to it. But for outsiders, it's really not look very convincing, but let's see what it does. So I want to derive the entropy, and for this, I know the energy of a black hole. It's very easy. Energy is just mc squared. And m is linear in the horizon, so it's proportional to the horizon, to the size, right? So now I'm asking myself, what could be temperature? How I would see that it's really temperature? Because it radiates, right? And so what it would radiate? So out of this size, h bar and c, well, this horizon already contains gravity constant. What kind of temperature I can build? Well, temperature in energetic unit, namely, it's something which having dimensionality of energy. How would you say that you have radius, you have h, and you have c? Well, if you just count dimensionality, there is only one combination of this. There is a P theorem. If you have grams, centimeters, and second, and you have three quantities, then you can build only one quantity. Well, so this is something very simple. It's always h omega, and omega in this case, when you have a speed, right? So how you create omega, right? You divide speed by size, right? You can say that this is the h omega of a photon having wave number 1 over r. And again, black holes, I mean, most of them are microscopic, so it's not that idiotic as it may look. So essentially, you say that your temperature in energetic units is hc over rh. But as we discussed, temperature is a derivative of what with respect to what? It is a derivative of energy with respect to entropy. And energy is RH, right? So what is this? Is mc squared. So energy is d ds. What stands here is c squared times m, which is RH, c to the 4 divided by g, ds. So you have dr ds is equal to 1 over rh. It's an equation which allows you to integrate it and obtain the following formula, which is called Wittgenstein-Hawking entropy for black hole. It tells you that it is, you see, R, it gives you squared proportional, so entropy is proportional to R squared. And what stands here in the denominator must be something which has a dimensionality of squared lengths, and it's called Planck, no white. Yep, okay. So this is GH bar. So this is called LP squared. It's a Planck length. Okay, this is a derivation which tells you that just for the fact that there exists a quantum mechanics, and whatever you take something and it's confined in size R, it has a kinetic energy or any energy which is related to this size in this way, right? So this is H, C over R. This is just a Heisenberg relation, if you wish, right? Simply. And for this, you need to now associate entropy with it. What's the most surprising part of this formula? Incidentally, it's the only formula in which all three fundamental constants meet. There are other formulas which are products of this. But what is really strange here? Yes, it's why it's called area law. That what it tells you that the entropy is not a volume, it's an area. Okay, so this is sometimes people, and there are unbelievable amount of speculations around this formula, and one of them is called holographic principle. Right? It tells you that because what is inside black hole is inaccessible, so what you see, you essentially see a degrees of freedom which live on your surface, and that's why. But on the other hand, you say, I mean, wait, this is black hole, but let's say I start from something kind of very large and dilute. I know that for all the other systems, my entropy is volume. It's extensive, right? And so now, what actually happens that from this R cube, I would get to R squared. And the answer is that you add and add and add your matter to your system. And at some point, when you add so much mass so that your size is already less than your horizon, it turns into a black hole, and from that moment, you stop seeing what is inside, and an entropy stop being proportional to the volume and start being proportional to the area. Okay? Which is still not yet a restriction on any entropy of any thing which is outside world. You say, okay, black hole, I understand. It's something closed, and I cannot look inside. I see only outside. So essentially what I see is just how many Planck lengths are right over there. But if I just take a usual body, which is not a black hole, and that's now let's do what is called Wittgenstein bound. Yeah, really. It's visible because I ran out of white. So Wittgenstein bound is exactly what comes out of this Gedanken experiment of dropping something into a black hole. Okay? And this is essentially an attempt to answer the following question. I'm just having some of the size R. Okay? Let's say I even have an energy. I know that this is a body of the size R, and I have an energy E. Is there any restriction on the total amount of information that I can encode inside this area using everything I could? photon spins every last quantum degree of freedom of the matter. Okay? So here is the equation which apparently must include fundamental constants. Apparently h bar, because it's quantum, right? So I am asking if there's anything s less or equal made out of it. Apparently, the larger is the energy over here, the larger must be the entropy, as long as the temperature is positive. So in a sense, I am asking, what is the minimal temperature, because that would give me maximal entropy. So what is the minimal temperature that something of the size r can have? Like, cannot go lower. Minimum energy, essentially. Entropy is dimensionless. So it must be your energy that you have here divided by some kind of minimal energy. But this minimal energy must depend on the size. What is it? Give me a formula. R. So I really, this to me somehow related to R, probably to H bar. So now its choice is to take G or C or G and C, both of them. And again, I'm not doing dimensionality analysis because it's really simple, to do differential analysis. But I want you develop physical intuition. And I already told you this physical idea, which I'm now about to use. Planck length, incidentally, has all three constants. But that, if I would relate to Planck's length, I would need to take r squared divided by Planck's length. Incidentally, this is something which makes sense. But for now, I'm trying to express not singularly in these r terms. It's a very good idea. It will appear 5 minutes down the road. But for now, I want energy here. So for energy, I need a minimal energy. And minimal energy is what I already told you about this longest photon that you can have, right? So if you have this r, right? So what you have here, you can have a longest wavelength there is just the size of it. And the lowest energy is, of course, hc over r. So what stands here is E hc over r. Okay? And this is something which is, you kind of get it almost for free, but then Wittgenstein said, let's consider it like this. Let's take this body, let's take a really big black hole, okay, and drop this into it. It's an elaborated theory. You can really do it adiabatically slowly, and you can try to describe all the process within general relativity. And remember that we still do not have quantum gravity. We don't have. But the whole idea is that you can, of course, this E is mc squared. So when you add this to it, what you add to mass is E over c squared, right? But your entropy is your of entropy of a black hole. It's your horizon square, which means that its horizon is linear with mass. You see this formula, RH is gm over c squared. So when you're adding this, and you assume, of course, at this point that this is small relatively to this, so you add this, you want entropy, you need to take this E over c squared, and this would be your delta S proportional to it, right? And so you can approximately say that this would be ME over c squared, namely you neglect term quadratic in it. And this is an increase of the entropy of the black hole. And, argued Wittgenstein, it must be lower than the entropy, it must be higher than the entropy of your body. You see? So that's an argument. So if you take any body, it cannot have more entropy that would be increase of the entropy of a black hole if you drop it there. Again, this is what I think it's a religious statement that we believe in the second law of thermodynamics. Okay, but and so now you get an inequality, which is of course is z, and then after that you say that my body to be dropped into black hole by itself should not be a black hole, right? So that gives you this inequality. Okay, so the inequality is like this. So this is E R over HC, but it's also less or equal than R squared over LP squared, which is black hole entropy. And first of all, this is a very important statement that it really demonstrates you that this black hole, in this sense, it's a maximum entropy which exists. That's why at this point you switch from cubic to quadratic law, and it explains a lot of other things. But at the moment, I really want you to look at it and just feel just, how that it's a restriction from above on the amount of information. Well, it's astronomically large, but it's not a point. It's a restriction from above on the amount of information that could be encoded. It's a restriction from above on any amount of knowledge that we can have of a given finite region of space. And it contains H, C, and G, all three fundamental constants that we have. Okay? And that's the reason I include it in the course on information theory. Questions? Let's meditate a bit looking at it, okay? Yes. Exactly, you're absolutely right. Amount of information is the number of questions that you may ask. If you want to count it in bits, that would be a number of yes-no questions. Exactly, that's the point. Think about it, a number of yes-no questions that have meaningful answers about physical region of space is finite. Black holes is a maximum. At a given region of space, generally amount of information is restricted by the information that is encoded on the horizon of a black hole of that size. That's precisely this meaning. Okay, so you take a region, you say, could I squeeze more and more? You say, conservation. No conservation, I'm squeezing, I'm putting more and more and more particle. At some point, too much, and I have a black hole. And that's it, that's the limit. Okay? Yeah. So now, as long as we already understand this bizarre idea that the black hole is very, very entropic object, this is the most thing. Now let's look at this, as I said, money, love, second law of thermodynamics, yeah, you need your personal. So let's continue to develop our personal relation to the second law of thermodynamics. The universe, first of all, when I'm explaining to myself why in the information theory I need to have gravity, I say that because a black hole is a door out of this world. The only one we know, incidentally. Then it tells us something about our world. But then, very natural, you ask yourself, okay, come on, but there was also door leading to our world, which is the Big Bang, right? So somehow everything entered this world through Big Bang. We know surprisingly well from experiments, from observation, what was the state of universe right after Big Bang. It was a very, very, very uniform state of a universe, right? And then when it started expansion. And then the same damn gravity started to do what is called Jeans instability, namely producing inhomogeneities in this distribution of matter. We know how small fluctuation were back then. We just measured them because we have light coming from a distant path, right? So now what we know is that the gravity started to create inhomogeneities. It's called Jeans instability. So if you have sufficiently large volume of gas, it's unstable with respect to, local contraction. Then it would start gravitating, and then gravitate even more, create a star. A star produce all the heavy element of which we consist. And bingo, just look around. We're very low entropic states. Each one of you. Incidentally, somebody asked me to give extra piece about biology. That's what I will talk to you, how really life is sustained far from equilibrium by lower entropic state. But then let's look at the universe as a whole and ask if the entropy of the universe now, with all this structure, look, we discussed it, that the uniform state has a maximal entropy. Any inhomogeneity is a structure, it's a lower in entropy. So what happened, did our universe as a whole break the second law of thermodynamics? Does it entropy now is much less than it used to be? What do you think? Well, the matter is, well, a matter essentially is not conserved because energy turns into matter, etc. But the point is that you can just kind of try to count, right? And just take a very big chunk of a space and say, look, 100 million years ago, there were no stars, or there were like, that amount of stars. Now there are more stars in this region, right? So what the hell? Star means lower entropy. It's more inhomogeneous state. I have a big chunk of galactic gas, and now when I look at it and I see that there is much less gas, and there are stars here and there, and some of them are supernova, and some of them already collapsed, etc. And I'm asking, what the hell? Is this entropy is lower? Because it seems like this universe creating structures all the time. And we are a happy product of this, right? Look, we are very far from a thermal equilibrium. We are very low entropic state, each one of us. So what the hell? Let's think. Look, if this is the main question of the universe, let's give it some time. Yes? Well, temperature changes definitely, but then on the other hand, you take a gas in some state, and if it's closed, then it could be, for example, I don't know, interacting and this part hitting this part, so it can change temperature, but you don't expect the entropy would drop. It's just a system, okay? Universe, just a system, okay? So wait. First of all, are you buying all the statements that the entropy decreased? Let's start step by step. So what's globally? What do you expect? The entropy of the whole universe. Let's say, you expect it to increase, that it's actually larger now than after Big Bang or smaller. What's your intuition? Don't think, just what is it? It's smaller or larger? Yes, your intuition is correct. Now let's start thinking why. Because that's how you work as a scientist. Like you give an answer, then you ask. This is very different. You aren't undergrads anymore. Okay? Right, it's really larger. So where it is? In the whole universe, not an area. So it's a very right intuition. It trusts your intuition. So entropy of the universe is larger, and so okay, you take a gas, it's expanding, its entropy usually increasing. Okay? So it's like, again, it's one thing that I promised to tell, that we are on a larga Enrico Fermi, and one of the best things that from Enrico Fermi that I learned, for example, is not only the Fermi distribution something, is the asking question. It's called Fermi question. Just Google it. Or ask ChatGPT, what is Fermi question? One of the Fermi questions was, where is everyone? He asked at some lunch, which was about, life in the universe. So where is everyone? Where is this entropy? Yes. Very good. Very good. Very good. It's absolutely incorrect intuition to thinking that the uniform space creates most entropy. What breaks this, generally, mostly correct, this is mostly correct intuition. You take a gas, it's in a uniform state, in its thermal equilibrium, you create inhomogeneity, it's lower entropy. But, again, what I'm now telling you is hypothetical, as everything related to quantum gravity at this point. But what most people who do this believe that most of the entropy of our universe is in which objects? Yes. Because every black hole is an absolute maximum of entropy. And just by it's absolutely unavoidable that the moment you start creating inhomogeneous meta distribution, you would create gravitational collapses, and sufficiently large amount of mass would necessarily produce black holes. It's totally unavoidable. And the most of the entropy of the universe is over there. So you were right. So it's really, this intuition is correct until you create a black hole. And then it's a hugely entropic object. It's a pure speculation, and yet it's very plausible. And it is at this point I really want to kind of finish all this. And if you want more, for example, some people ask that on Friday during a discussion, if you want, I can give you a little bit about, genetic code, kinetic proofreading, this, biological side of it. Or if you want something else, you can look in the book. But now let me spend the last 2 minutes just reiterating what I want you to take home. P log P. Right? So the most kind of thing is just you take log of it because of this intuition that independent probabilities are multiplied. And it's really not necessarily independent probabilities of different events. You can do Markov chain, and this independent probability would be transition probability. Or you can do something else. But you like multiplying probabilities and taking log of it, and taking many, many terms on this sum, and thus using a law of large numbers. This is a very simple and unbelievably powerful idea. Right? It's most of physics, of statistical physics, stand on it. And second thing that I want you to remember is P log P over Q. That's how you compare true distribution with your hypothesis. It's called relative entropy. And I did not, unfortunately, derive this general uncertainty. It's all derived using relative entropy. Because when I really teach this course, I'll show you how powerful is this instrument. So I was just, hand waving. But so, P log P log P over Q, and F E minus TS. This is 3 most important things. And if you look at, you see some, great scientists, and you think that they think in some kind of complicated ways that simple people like us can understand. No. People who really, and I, in my life, know several really great scientists, they all think in a relatively simple way. But this it's like, Lego. When you're a kid, you build from Lego some kind of complicated things. So there are several elements on which you're absolutely sure. You just throw the light and it's here. And you know how it's connected to others. And from these simple elements, you create your buildings, right? So this idea that E minus TS, whenever you have conflicting things, you negotiate them by a method of Lagrange multiplier. you look for extremum of S under condition of energy, or you do any other things. So this is the third thing that I want you to remember. Questions? You look sad. There are only three things. It's not that much. 3 lectures, 3 things. First lecture, P log P. Yeah, the quantized area on a black hole is this guy, which is this. Yeah, this is, if in the usual quantum mechanics you have PQ equal to h bar, that's your elements in which your phase space is broken. Now here on this surface, this is your elements, okay, which you count, and that's many elements, that's your entropy. Okay, good guys, thanks a lot. It was a pleasure to this, and see. Yeah.
Thank you for the lecture, and yes, we have question time tomorrow at 2:30 for further questions. I also would like to remind you about this afternoon, the first lecture of Jabodimaya on the at 2:30.
Today is 2:30, да?